I guess many of you know, who's at Agra at the Albag University. So let me begin with some introduction, at least some aspects of Loga's talk I can use. So the sum rules we are sort of interested in deriving for general conformal field theories in arbitrary dimensions is of the following structure. So there's an integral over the frequencies, and maybe there's some weight, and there's a density function. And usually the schematic form of these sum rules will be some form like this, where rho of omega is the imaginary part of the retarded Green's function of certain operators. We will specify the operators soon. So it's an integral expression like this. And you see this is a retarded correlation function in thermal state, which, as Loga said, is difficult to obtain in general on the lattice, for instance. So this, we will try to get sum rules of this kind, which is equal to one-point functions, expectation always value of one-point functions. So these are the kind of sum rules, schematic form of the sum rule which we'll be interested in. And these are, and as we saw in Loga's talk, such Green functions are very hard to evaluate on the lattice, and he mentioned it briefly. And one of the things about the lattice, if you have such relations, it actually puts constraints on the spectral density. It's called the spectral density usually. It puts constraints because these are reasonably easy to calculate. And you will see, actually, you will see as the derivation progresses, that there is a certain information about, so let me first say relate. So some rules relate two-point functions to, I hope people can see, two-point functions to one-point functions. And as you'll see, as the derivation progresses, you will see that there is an information about three-point functions of the theory also. So it'll have three-point functions, information of the theory. Okay, you'll see that as it goes. As I mentioned, it constrains the two-point function in some way, even though we do not know much about the two-point function. Okay, and also, as we've been hearing for some time, that such rules go beyond hydrodynamics because it involves integrals over the full frequency domain. So what we'll be interested in is some rules of this kind for arbitrary conformal field theories, d greater than or equal to 2. But I will illustrate the derivation for d equals 2 so that you get just the aspects of the derivation. And since we are interested in certain universal sum rules, in general conformal field theories in arbitrary dimensions. So we will look at an operator which is universal in all the conformal field theories, which is the stress tensor. So, the particular operator is, say, T mu of stress tensor. And we will specify the correlator, though we have done some calculation. This is work in progress, so I'll report part of it, though we have. So we will actually describe, I will actually talk right now about this following retarded Green's function. So it's the correlator. The correlator we are interested in is the stress energy tensor in, say, the XY stress tensor. This particular component of the stress tensor, and its Fourier transform. Let me just define this before I go ahead. So the frequency Fourier transform at zero momentum is defined as follows. So we'll be interested in this kind of, this is the particular correlator we'll be focused on most of the talk, almost all the talks. Maybe towards the end, if I have time, I'll indicate the results with the other correlators. So before we go ahead, let's just briefly recall how some rules are generally defined. They're consequences of analyticity, actually. So consider, so just let me just briefly describe in general how such a rule is obtained. So consider function g of omega, which is, this is a general mathematical derivation, which is holomorphic in the upper half plane, okay, including the real axis. Okay. And say it has such convergence properties. Precisely specifying it, we will refine it as we go. So it goes to 0 as if imaginary omega is greater than or equal to 0. Okay, a large omega in the upper half plane, it goes to 0. Then by Cauchy's theorem, so let me just call it CT, Cauchy's theorem, G of omega hat plus I epsilon, let me just define. I'm sure everybody here would know this. They must have learned it. As Shiraz said in 11th standard or 12th standard. I don't know. Yeah, maybe one learns it at that time. So Z minus omega hat. Okay. And epsilon is real. Epsilon is greater than 0. Omega hat is real. So this is Cauchy's theorem. Basically, you're completing this. This is a holomorphic in the upper half plane. You're doing a real integral, but you're completing it in the upper half plane using the convergence property and picking up the pole here. That is this. Okay. And then, of course, if you have, you can apply it again, and you have 0 equals 1 by 2 pi I minus infinity to infinity G of Z dz by Z minus omega hat plus I epsilon. Yeah. So you have this particular property also because this is down, this pole is below, and so it's 0 here. So if you take this 1 plus star of 2, you just take this plus the star of this, okay? Then, and this is real, not this is real, and then if you take it, you actually get G of omega hat. So I'm doing this operation 1 plus 2 of star 2, G of omega hat. Okay, now I can take the limit, 0 plus. And you see the imaginary part of this function easily comes about, rho of Z, so which is the imaginary part of G, because you see that when I take the star, okay, I get the minus sign here, okay, and this becomes minus, so it, like the denominator becomes the same, and so we just did. So this is sort of the sum rule, and just writing it a little bit. This is a dummy variable after all, and just writing it in a nice form. And in fact, the sum rule we'll be interested in when omega hat is equal to 0, limit epsilon going to 0 plus d omega by pi. And rho of omega, let me define so that for completeness, is 1 by 2i g of omega minus g of omega star. So this is sort of the naive derivation. And usually such retarded Green's functions, Fourier transform, is sort of expected to be analytic in the upper half plane, basically because of causality. And we will assume that. Okay. There are some cases in holographic situations you can prove it, but we'll assume that it is analytic. It has this nice property. Okay. And what we will do is basically now trying to focus to derive such some rules for this particular correlator. And what we need, of course, is first to test whether such correlators, Fourier transforms constructed out of this correlator, converges in the upper half plane. So that's the first thing we need to test. And for that, of course, we need to somehow analytically continue these correlators into the upper half plane. Okay. For that, what we will do is basically use a well-known result. In fact, it's part of what Sam talked about. It's an analytic continuation in imaginary time. And there is a relation. It takes a couple of steps to prove it, but maybe I will just sort of state it. So if you evaluate the retarded correlator this is the temperature, this is the temperature, and if you evaluate it in this particular temperature, this particular imaginary temperature, it is the same as the Euclidean correlator at the max square of frequency. So we will use this relation. Yeah. I mean, if people are interested, I can try to prove it, but let me just go ahead using this relation. And what this relation, hints at a distinguished analytic continuation. And what we will use is that. So we basically, to investigate the retarded correlator at omega going to infinity, we will just appeal the Euclidean. Use the Euclidean correlator at large omega. So now there is further. Yeah. Yes. Yeah. At these frequencies, yeah. So there is that phase becomes 1, yeah. Becomes 1, yeah. Yeah, beta, I think the phase, 2 pi I omega n, I think, omega n becomes 1, yeah. Yeah, that's actually. So, so let me just assume it and go ahead. And so we are also interested in trying to check this convergence property, right? To apply such general this Cauchy identity. So what we had to do is first study this correlator. Okay, we'll use the Euclidean continuation at large frequencies. Now, so for that, so consider so there is a simplification when you look at this correlator at large frequencies. Consider the Euclidean correlator in position space. And if time intervals or something is much smaller or distances are much smaller than beta, then, the OPE, the operator product expansion, offers a good asymptotic expansion. So that's what we're going to use. We're going to, so therefore, at high frequencies, inverting this relation, high frequencies, we can replace the Euclidean correlator, at least for trying to find the asymptotic structure by the operator product expansion. So now let's try to get the asymptotic properties by the asymptotic operator product expansion. I know I'll be erasing a lot, but I think if I write it big, maybe people here see it. So let's get a sort of rough idea first, okay? So let's look at, generally, now I'm not even looking at components, just the scaling behavior, okay? So the Tx T0 OPE, look at the TT OPE. Okay, so of course the first term in D dimension is something like x to the power 2d, or conformal theory. It'll be x to the power 2d. Then there is a term, if you are not so familiar, you can just remember your two-dimensional conformal field theory, which is what the example I will sort of a little bit work out is. And then we have x to the d. So this is sort of the rough structure of the OP. Of course, there are sub-leading terms. But you will see that these two are the ones crucially important for us. So this is the sort of, and this is in fact, and there is a tensor structure here in general. Tensor structures. Here there's the tensor structures. And all of these tensor structures are scaling dimension 1. Okay, that's the rough structure in arbitrary dimensions. And if you imagine doing a Fourier transform, so basically, do this operation. You do this operation, and you will see the scaling dimension of the first term. You can just do some scaling and show that it's roughly omega to the d. It's omega to the d. Okay, just scale out everything and just, it's omega to the d. So it diverges actually. So the first term diverges, in fact, you'll have to sometimes put a cutoff and there is some cutoff kind of function here. It diverges. The first term diverges. So somehow, if you were just the first step itself of doing this, this term basically diverges. So we need to somehow subtract this to appeal to the Cauchy's theorem. We need to subtract this. So, but we will see how to do it. So let's go to the next structure. Okay. So the next structure again is x to the d. And suppose you are in a thermal state, for instance. This will generally have expectation value, at least the diagonal values will have expectation value, the energy and the pressure, they'll have expectation value. And a Fourier transform of x to the d, roughly scaling wise, is omega to the 0. So this actually again produces a finite term. It doesn't die. It produces a finite term. So again, somehow we'll have to subtract even this, okay, to sort of appeal to the Cauchy's theorem and get the proof. So there are two terms. The next you can see actually are subleading. So we'll assume the stress tensor is the only operator which gets expectation value, and the next are subleading terms. So, so the first assumption in our sum rule seems to be violated for deriving the sum rule. So somehow we'll have to subtract. So one of the ways to subtract it is basically realize that this is basically the 2-point function of the theory at 0 temperature. Okay. So so we define first thing, we modify this. We look at a particular Green's function, change simple man's resolution. So this is the t not equal to 0. Let me t not equal to 0 minus t equals 0. Okay. This takes care of that first divergence because this has exactly the same divergence and it cancels it off. It's exactly the same term. And then we'll also have to subtract out the finite pieces which arise because of the expectation value of the stress test. So we'll have to subtract this out. And if you subtract this out, this rest of the terms are subleading. And then we will sort of do this. And so therefore, in this so this is the scheme. So what we will have is delta gr omega is equal to 0 is equal to, so we can apply this, the Cauchy theorem on this, and we will, and what we are trying to derive is basically the RHS or LHS, this part of the answer. So let's work this out in 2D. So we'll work it out in 2D before we generalize it to arbitrary conformal field theories in arbitrary dimensions. So 2D. So the way I'm going to write OPEs might not be very familiar because there might be some. I mean, you must be familiar with such an OPE. Such sort of OPE, you must be familiar. C is the central charge, but you can convert this into T and X space, for instance, or T and X space, and in fact, the stress tensor here. I mean, if you recall your original, I mean, string theory and initial lectures are confirmed, there will be a 4 pi del by del G mu nu, and we won't put this 4 pi. We'll just use the usual definition, and converting this OPE basically into TTX. So this is the correlator we are looking at, TTX, TTX, TX, 0, 0. Okay, if you carefully do it, there is 4. Yeah, so there's this divergence piece, which anyway we are not interested in. Basically, roughly, if you want to sort of work it out in your head, actually TTX is I TZZ minus TZ bar, TZ bar. You can work it out in your head. So there is sort of terms like these, so which anyway we are not very much interested in, which we are going to subtract out. But here, The finite piece is of this kind. There's an expectation value. So this is the finite piece, and in fact, if you because you are doing Fourier transform, you actually keep, you will have to, though it doesn't contribute, but you will have to keep track of contact terms if there are, and in fact there are contact terms here. Let me just write it. Though people are not very familiar here, but there are contact terms actually. And it doesn't contribute here, but I'm just illustrating it for the general story. So there is a term of this kind. So it looks a little funny, but you know, in Fourier space, they look nice. Del T. And there's a delta function. And the complex conjugate of that. So there are these terms also, but in general, in higher dimensions, these terms will play a role. And the Fourier transform of this, actually in the large frequency limit, they vanish. But the other terms, one by dt, yes, yeah, there is these terms. Yeah. No, well, the reason is that because you need, yeah, so for instance, if you remember, the trace anomaly comes for such terms. It's a trace anomaly. See, if you have, look at this correlator. This is actually dz, this is a contact term. Yeah, I know people will immediately ask me this. So for instance, this is a contact. Yeah, 1 by z. Yeah. Yeah. Right. Yeah. 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 So, yes, yes. Well, yeah. Yeah. Okay, I don't know. I called it because of the delta function. Well, yeah, might not become. But anyway, it, at high frequency, it sort of, yeah, the reason this is required is because of the conservation laws. If you hit del T, you have such terms actually. So these terms sort of are not contributing. Hey, where is my? So basically what we need is basically the Fourier transform of this particular term. And let me work that out. One can do that Fourier transform explicitly. And if you do the Fourier transform, so ft of e to the I omega t plus I px, t squared minus x squared plus t squared the whole squared. So this is 4p, 4 pi, t squared minus omega squared. So as expected, it's scale invariant. And at high frequencies, that omega goes to infinity, it's minus 4 pi. So the delta GR, which we are constructing, okay, so this is the finite piece. It's minus 4 pi times this, this particular term. So the constant term is minus TT expectation value. And this is energy, and this is pressure. So that's the, it's in a thermal state, it's energy and pressure. So it's basically minus energy plus pressure. That's the finite term. So, but we have to subtract out these finite pieces. Okay. So delta GR so delta GR is basically, as I said, at omega t is equal to 0, t not equal to 0, minus GR omega t equals 0, which removes that first term, plus epsilon minus p. Now, the right-hand side of the sum rule, is basically evaluating this at 0 frequency. So it evaluates this at 0 frequencies, and of course this is some, it's basically omega squared kind of term, and that goes to 0 at 0 frequency, and this one can be evaluated using hydrodynamics. At omega is equal to 0. So we need, okay, let me step again. We need delta GR at 0. At delta GR 0, so this goes to 0. This we can evaluate using hydrodynamics because it's basically TTX correlator at 0 frequency, which is pressure. At omega limit, omega going to 0, it's pressure, and this becomes basically, this is pressure, and this one is plus epsilon minus P, cancels. So, so the sum rule in this case is quite simple. Actually, I've not seen it anywhere, but I guess it will be there somewhere, epsilon. So this is sort of the sum rule in this particular case. And you see that in this derivation of the sum rule, in the derivation, it is the high frequency, actually high frequency term which sort of stayed behind in some sense. It came from this constant piece. Okay? So therefore, it has some information about the operator product expansion, and therefore some information about the theory. In particular, the 3-point function in this particular case, it's the TT OPE giving rise to the T. So it has that particular information. And so the general feature one must keep in mind is you need high frequency behavior. And that's of course controlled by the conformal invariance of the theory. So it's, in some sense you can say, you know, spectral densities, what are the constraints, some limited constraints using conformal invariance on spectral density. You can formulate it in this way also. So the high frequency part affects the RHS of the sum rule. In this case it's RHS here. RHS of the sum rule, and is basically controlled by the OPE of the stress tensor. So of course now if you are going to push this to higher dimensions, we need the OPE information about stress tensor in higher dimensions. And that, let me write the structure, that has been worked out by Osborne and Petku in the early 90s, and you know, has played considerable role in ADS-CFT, I think. So, so we now in B greater than 2. So we need details of the OPE coefficients. Oh, 15 minutes of stress tensor in higher dimensions. So basically, it's of the same form which I wrote. Let me write it. One particular term. 15 minutes. There's a term like the central term. Again, I'm just writing this. I'm writing the sort of. This is x to the let's call it x. This is the distance to d kind of term, and then there is this particular term which is sort of important, as we saw in the two-dimensional case. This particular term, but all these coefficients are known. They have been worked out by Osborne and Petku, and they are stated in certain, for higher dimensional theories, higher dimensional conformal P theories. They are stated in certain numbers, almost analogous to the central charges. They are called coefficients A, B, and C. But just to get an intuitive idea, I will say it in D equals 4. just to give you a flavor of it, because many people might have not seen this in high dimensions. So just to get an intuitive flavor, so the general structure of the 3-point function, this basically is controlled by the 3-point function in 3 stress tensors, can be decomposed into, 3-point functions. This is say d equals 4, free scalar theory. So take the tensor structure of the free scalar theory and ns times that. So there's a number like that. So I say it has ns. There's a number. Free. This is Osborne and Petku. Free vectors plus nf. Free fermions. So, and in fact, the coefficients we'll be using are something related to ns. So they call ABC. So any 3-point function, any conformal field theory in D equals 4, for instance, can be written, decomposed like this. And you can relate these numbers to some coefficients which are much more, which are useful to write these relations, which I'm going to write down. So just so there's a linear relation between these ABC and NS, NV, and NF. So I'm just writing the relation. So there's a relation relating these things. So we'll actually be working in some languages A, B, and C. Even the CT has a linear relation in terms of A, B, and C, and D dimensions, various dimensions of the theory. So similarly, there is a relation in higher dimensions. You can parameterize this 3-point function of our stress tensor in terms of these coefficients A, B, and C. So one of them, I mean, these are the Maldacena-Hoffman coefficients actually, and they have bounds on those things, of course. So this is, it's nice to write it like that, but we will be writing the relation in terms of A, B, and C. So, so in fact, this has like huge number of tensor structures. To be precise, there's a lot of tensor structures, and they are complicated functions of dimension 1 kind of functions. The dimension to the 1 functions. And the thing is that, okay, given a particular kinematic structure, say xy, xy, you can take this and do the Fourier transform just like as I demonstrated in 2 dimensions. You can do this Fourier transform, take the high frequency limit. I will just state the results actually. You can take, and because I have short time. No, they depend on the theory. You can compute them for various theories. It's like the central charge. I mean, like parameterizing the these 3 conformal structures. So you can compute them for definite theories, and we will do them. We have like a little bit more. I will show some examples. And so, so the constant term which I talked about here, okay, let me write them out. So there is some formula for the constant term. Let me call the constant term A, okay, and big A. And the constant term, if you calculate it for the xy correlator in the large frequency limit, it's some formula in terms of A, E, D plus 4, so it's minus 4. Plus D to B minus C. So there's a formula which you can get. And there is a contact term. Here also there is a contact term. Okay. Let me call that contact term B, which is also constant here. In the 2-dimensional case, that didn't play a role. But here it is there. And it's 2A plus B minus 2 plus D minus CD. I'm writing this in terms of pressure for a reason. This is written in terms of the energy. 2B minus C into 1 plus D. It's the same denominator. It's basically from the CT term, pressure. So, and again, so these are the constant terms. These are the finite terms. Again, you define delta G omega, the frequency sum rule, gr omega at t minus gr omega at t is equal to 0 minus this A plus B. So, and this is well defined. You can apply the Cauchy's theorem. And therefore, the right-hand side of the sum rule is delta G at 0 frequency, which is basically the value, this is G, the value of this at 0 frequency, this is pressure minus, and this is 0 and A plus B. So there is, you can write it, so it's P minus this two terms, that's the answer. So it looks, okay, you can write an expression and it's supposed to be valid for general conformal field theories. But one of the things before I go ahead and like check it with examples, one of the things is that this term, this without the contact term, if you look at this term is just now an observation, most probably there must be some reason we haven't understood it. This term is basically the Hoffman-Maldacena coefficient. When he looked at energy flux, so he looked at certain energy fluxes created by states which are excited by some by stress tensor themselves. And this is one of the coefficients. It's the one in the tensor channel. So this is that particular coefficient. So there is this observation. This observation is there in the other channels also. So this high frequency term without the contact term is basically that. Okay. And so let me just so rather than putting all this together and writing an expression, I will apply it for various cases, various conformal field theories which a favorite of ours. I will apply it and see what we get. And then there will be some small contact I can make with old work. Right. Yeah, that's right. So they were looking at some of the poles. That's a different kinematic regime. At omega equals P. And somehow they identify some of these coefficients. But even at the high frequency limit, these are the same coefficients which are coming in. There must be because of some complex analytic structure actually, because maybe they're looking at zero frequency, some kind of poles, and this is like high frequency, and there must be a relation between those two things. We haven't done that. But let me just put these two together and see what we get for various theories. So D equals 4. So of course the favorite theory is N equals 4 Yang-Mills. Okay. And let me write down, so basically you have to put D equals 4 in this, D equals 4 in this, and evaluate ABC. Of course ABC you can't easily evaluate, but you can evaluate it in the free limit. AB, and this is the contact, this is the pressure term P. Let me just call it low frequency. That's always P. And this is the RHS of the sum rule. So N equals 4 Yang-Mills. We know the matter content. Okay. Some 6 scalars, 4 Majorana fermions, and a gauge field. And you plug in, and at the free limit, you can compute this ABC. There are formulas for that. You can compute that. And the numbers are sort of funny, but let me give the numbers at least for this case. A is minus 16 by 9 pi 6 n squared minus 1. N is the number adjoint n squared. B is 90 minus C. So they are sort of odd numbers. But if you substitute it A, this turns out to be 2 by 5 epsilon. 2 by 5 epsilon. And this turns out to be minus pressure, which cancels this pressure. And the full answer is 2 by 5 epsilon. 2 by 5 epsilon. D equals 3. And of course, one expects this coefficient is not renormalized, it's agreeing with. And in fact, there is, okay, I will mention the gravity calculation, and of course, it lands into this. So let's look at D equals 3. So there is the favorite theory, M2 brane. 8 scalars, 8 Majorana fermions. You can compute ABC. They are also sort of funny numbers. 27 by 8 4 pi to the cube. B is minus 117 by 8 pi to the power of cubed. C is minus 81 8, 5. So this is the M2 brane theory, for instance. Again, this A is actually, okay, this is reasonably. So let me write the gravity answer from here. So there is a computation of this you can use in gravity also. In fact, the gravity computation we did earlier with Sachin Jain and somebody talked to it earlier. And in the gravity, and it was also done by Son. We generalized it to arbitrary dimensions for these particular theories. In the gravity calculation, you get here 2 by 5 epsilon and minus P and P, of course, and 2 by 5 epsilon. This is the same. And there are two ways of doing the gravity calculation. I should just remark before mentioning everything. One is actually computing this retarded correlator explicitly in a black hole background, analyzing its high frequency behavior. And for that, you just need to set up some Pepperman-Graham kind of methods. And you can find the first subleading term. And you can extract these terms. And you will be able to, you can see that it falls into the same thing. There is another method of finding the gravity answer, is basically computing the 3-point function in ADS. Stress tensor 3-point function in ADS directly. It was done by Aritinov and Frolov in the beginning days of ADS. And you can get these values directly there. And plugging in, you get the same answers, of course, for consistency. And D equals 3, let's do this. So in the free limit, if you compute A, P, and low frequency term, of course, is always pressure, and RHS of the sum rule. So I have 2 minutes. So, so this is 0 actually, because these are like theories without vectors, and this particular channel is saturated. So this is 0. This is minus P quad 4. Pressure. Okay. And you get 3 by 8 epsilon here, and here. So ABJM. Let me just classify everything. All the theories, all the favorite theories. ABJM is also the same. 0 minus P by 4 P 3 by 8 epsilon. And ABJM you can put, and gravity, of course, is just like the way it behaves there. 3 by 8 epsilon minus pressure. So finally, it's 3 by 8 epsilon. And let's do large N Chern-Simons, which is sort of a favorite of people here. And here you see, I mean, and at our arbitrary coupling. So let me give the ABC for the largest large Chern-Simon. So it's 27 by 32. So here there is some coupling dependence. Because here there is not agreement. Theta is pi n by k. N is the n of the fundamental fermions, k is the level. So large N Chern-Simons coupled to fermions. So it's 9/27. This is 27. So it's 9n minus 17, I think, if I copied it correctly, sin theta by 64 theta. And C is minus 9n 17 plus 15 cos theta sin theta by 64 theta. And if you look at the ABC, capital AB, capital BC, this is 0 again, because again these are theories without vectors. So it's minus P 1 plus cos theta 3 cos theta. And pressure is always the low frequency term. And together it is epsilon by 3 plus. I've converted into energy. And okay, there is some interesting behavior at cos theta is minus 1/3, which agrees with the gravity result, 3 by 8. So M theory, the M5 brane also, if you sort of substitute, you will get similar patterns. And the general behavior, so let me just conclude with the M5 brane and the general behavior. So the M5 brane, A, B, C are quite awful. 2592 by 100 pi to the power 4. B is minus 7848 by 100 to the pi to the 9, I think, pi to the 9. 5 to the 9. C is also quite awkward. 8, 100 pi to the 9. But if you plug in, this becomes 3p by 7 minus pressure, of course, from that term, from the contact term, pressure, and totally it's 3p by 7. Gravity also mimics exactly 3p energy. So 3 energy by 7, I've written this in energy, minus pressure, and so the general behavior seems to be, so for a conformal theory, I mean, these coefficients are not renormalized, that seems to be the lesson. And there is a very nice pattern which agrees with gravity, which is d divided, the sum rule is 2d divided by t plus 1. So that's sort of the lesson. And we are actually analyzing this in the other channels. And in the other channels, one gets the, I think at high frequencies, there are terms which are basically the other coefficients of Hoffman and Malderson are coefficients. And in fact, one of the things we are probing are the parity odd channel in the Chern sequence. Yeah, this M7. These 6, right? 6. Yeah, so 6 cancels in 3. 3 epsilon. This, yeah. So, I mean, if you just study the minimally coupled scalar in this, of course, it doesn't know anything. It just knows something about the dimensions. And you see this expression. And of course, this is the sum rule. I mean, it's the validity of our sum rule. I mean, it's some mess for any dimensions, and you just plug in the values of the theories we know. It lands into that particular answer. So it's sort of, yeah, we are looking at the other channels, in particular the odd channel of this Chern-Simons theory. Yeah, ABC computation. So that will go like, for instance, in just to say it's gravity computation, if you look at the ABC coefficients of the gravity directly by looking at the 3-point function, for instance, in the M2 brane, it will scale like n to the 2/3, And for the M5 brane, it will scale like n cubed. But if you like compute, and because this is a ratio, they become this nice numbers. They're all arranged on. Yeah, just ADS, yeah. In fact, they have done it for arbitrary D, okay? And right now, okay, we are in that process. We didn't plug their values for arbitrary D and check, we get this answer, this D by 2D. We haven't checked that yet. Yeah.
ABC should have to satisfy some constraint.
We don't have any constraint, actually. Yeah, it just gives it in terms of ABC.
No. So if you calculate P minus A plus B.
P minus A plus B. Yes. Yeah.
And so that is what is supposed to give you this answer?
Yeah, so that gives this answer. I mean, some complicated answer for any arbitrary conformal field theory. But for the theories we know for gravity theories, which we know there is a dual, it's supposed to be this D divided by 2D plus 1.
So that should be a condition on ABC. What is the condition?
Well, yeah, we haven't written it down. There should be a condition now. Yeah, in fact, for instance, that is what is surprising. In the fundamental Chern-Simons theory, you compute it, it is this answer, epsilon divided by 3 plus cos theta. And theta is the coupling. And this very peculiar value for the coupling, cos theta is minus 1/3, it actually reduces to 3 by 8 epsilon. Yeah, I don't know. Yeah.
No, so the statement that this is equal to this d epsilon by 2d into d plus 1 is a constraint on the ABC coefficient.
Yeah, it's a constraint on it.
It's a condition on ABC coefficient, and somehow that condition seems to be always true for things with gravity.
Gravity dual, yes.
But I'm just asking whether that is true.
In no, we have just checked it for gravity duals. I mean, and it is true. I think for all the theories which admit gravity duals. Yeah, yeah, that I think will be true.
But it will be interesting to see what the.
Yeah, in general, the condition. Yeah, for instance, in the fundamental chance moments, you get this particular, I don't know, cos theta, particular value. So, of course, we are examining it in the other channels, this whole things in the other channels, as well as the parity odd structure. By the way, I should acknowledge this is a result of a bus ride with Loga, where he asked about constraints of spectral densities using conformal. It was the result of those investigations. Okay. And since I'm the last senior speaker, let me thank Loga and and Suvrat for organizing this very nice meeting.